So, in previous videos, we talked about matrix operations and we showed how to talked about addition and subtraction of matrices, uh, operations with scalars, and multiplication of matrices. But we didn't talk about division of matrices. And we might have a situation, say, where you have a matrix A and you multiply it by a matrix X. I'm going to make that's a capital X. And then say this equals the matrix, maybe the matrix Y, capital Y. I'll put a little tail on to represent that. And so yeah, say you want to solve a matrix relationship like this. Now, and in an analogous way, that's like saying, say you have 3 times x equals 6, for example. Well, what do you do there? You divide 3 by 3, and so you do the same thing on this side. So you solve something like this in the real number system with division, and so then you get 1 times x equals 2, or x equals 2. So this is analogous to what we're trying to do. So we need to come up with a way to do something that's like division in order to solve this relationship. All right, well, the first step is let's discuss what we call the identity matrix. So the identity matrix is a matrix that has 1s along the diagonal. It's a square matrix, and 0s everywhere else. For example, let's look at a smaller matrix. Let's look at a 2 by 2. 2 by 2 identity matrix would look like this. And a 3 by 3 identity matrix would look like this. So on and so forth. We can make them bigger and bigger and bigger. Well, the identity matrix has the property that when you take the identity matrix and you multiply it by a matrix, then you get the original matrix back. So let's try that in just a simple 2 by 2 situation. So say we have 3, 4, 1, and 6, and we multiply it by, let's do it the way I have it shown up here. Take the identity matrix and we multiply it by this. So 1 times 3 is 3, 0 times 1 is 0. 1 times 4 is 4, 0 times 6 is 0. 0 times 3 is 0, 1 times 1 is 1. And 0 times 4 is 0, and 1 times 6 is 6. So you see what we result. Our result is 3, 4, 1, 6, which is the same as our original matrix. So that's what the identity matrix does. We have another matrix that I'm just going to call the inverse matrix, and you're just going to have to believe me that it exists. Inverse matrix. And the way the inverse works is if you take a matrix and you multiply it by its inverse, you end up with the identity matrix. This is cool because if you can figure out what this identity matrix is, you can multiply it by our original matrix, and you're going to end up with an identity, which is kind of like a division, analogous to a division going on there. So, for example, if A is 3, 1, 2, 1, then if it exists, the identity matrix for this, and it does exist for this matrix, is 1 minus 1 minus 2, 3. So that means that if I take A times A inverse, I should get the identity matrix. So I'm saying 3, 1, 2, 1 times 1 minus 1 minus 2, 3. So this equals 3 minus 2, and then minus 3 plus 3, and then 2 minus 2, and then minus 2 plus 3. You can see 3 minus 2 is 1, minus 3 plus 3 is 0, 2 minus 2 is 0, 1. So it works. Now you might be sitting here and you might be saying, well, that's kind of cool, but where the heck did you get this identity matrix? You just kind of like pulled this out of a hat. And well, at this point in this class, that's what we're going to do. We're going to pretty much pull it out of a hat. So if you're given a matrix, say A equals 3, 1, 2, 1, and you need to determine what the identity matrix is, then what I want you to do is I want you to use an application. Now you might be rolling your eyes, but this is not as hard as it sounds. For example, just go to Google and type in matrix or type in inverse matrix calculator. Here, I've done this before, so it pops up. Type in inverse matrix calculator and look and see what you got. I'll just pick the first one. And here is an application that does a matrix inverter. You type in, put in the size of your matrix, 2 by 2. Matrices need to be square matrices to have an inverse. 2 by 2. Then it tells you to set the matrix up. And let's put in the one we had, 3, 1, 2, and 1. And of course you can have your elements be anything. Now the inverse doesn't always exist, but if it does, this will find it. And we'll calculate this. And here it tells us the inverse is 1 minus 1 minus 2, 3. And that's just really the best way to do that right now. There are other ways to find the inverse, but we don't really have time to go through all that stuff. Okay, so now that we have the ability to find inverses, we can deal with this problem here. Watch, 3, 1, 2, 1 was our A. We're going to multiply it by this X matrix, which was A and B. And over here, we had just 2 and 1 in this matrix. I forget, did we call it something? Oh, we had the X and Y. So I guess we called this Y. Doesn't matter what you call your matrices, actually. Okay, so how do we do this? Well, if we could turn this into the identity matrix, then we would be able to take that and multiply it by this, the identity matrix by this, and we would have just this column vector. So let's do that. Let's take A inverse and multiply it by A. So A inverse was 1 minus 1 minus 2 and 3. Multiply this by A, 3, 1, 2, 1, and keep this. But since we multiplied this by that, we have to pre-multiply this by the same thing. So here's A inverse again. Since I multiplied by A inverse over here, this is new to this equation, I have to do it over here. But at least I have numbers over here I can operate on. Okay, well, we know this equals the identity matrix. You can work it out again if you want to. And what is the identity matrix times any matrix? It is that matrix. So now over here we have to actually do this operation. So we have to do 1 times 2 plus minus 1 times 1. That's that. And then for our second, we have minus 2 times 2 plus 3 times 1. So simplifying this equals 2 minus 1 . This is still the same element, 2 minus 1, and minus 4 plus 3. I'll do this and then I'll go back and check for mistakes. So this results in 1 minus 1. So now we're done. What does this say? Well, this says AB equals 1 minus 1. Or A equals 1, B equals minus 1. Pretty slick, huh? Well, now that we have the ability to take the inverse of matrices, we can use this to solve systems of equations. For example, let's look at this. X plus y equals 3 minus x plus 3y plus 4z equals minus 3, 4y equals 3z, 4y plus 3z equals 2. This is a system of 3 equations with 3 unknowns and 3 linear equations. We can use matrices and inverses to solve this. Let's set this up so that it has the form of A times an X matrix equals B or Y. So let's let our A matrix equal the coefficients in front of the variables over here on the left side. For example, we have 1 X, we have 1 Y, and we have 0 Z's. For our second row, we have minus 1, 3, and 4. And the last row is 0, 4, and 3. Make sure you keep your X's, your Y's, and your Z's all straight. Okay, for the X's, we have simply X, Y, and Z. Notice if you take A matrix times X matrix, you get these 3 equations. Finally, B equals 3 minus 3 and 2. So in order to solve for X, Y, and Z, we merely need to find the inverse of this A matrix. I used an app and I found this as my inverse matrix. Normally they're pretty complicated. So I take A inverse, I multiply it by A, I get the identity matrix times X, Y, Z. Then I have to make sure I pre-multiply this matrix by the inverse. Can't do it after, you got to do the same thing. If this was before, you have to do this before. I do that multiplication, I get this, which simplifies for our final solution for X, Y, and Z as 1, 2, and minus 2. And I don't have time, but you can take these values and plug them into your system of equation and check your results. Pretty slick, huh?